So today we will be discussing Fisher's linear discriminant analysis, and this is another linear method for dimension reduction. So what's the difference between LDA, Fisher's linear discriminant analysis, and PCA? Answer is the PCA works for unlabeled data, whereas LDA works for labeled data where the data belongs to different classes. And you should know that the total number of classes is discrete, so it's not a regression problem. So LDA is for data that needs to be classified. And at first, in this analysis, we shall consider two classes, and then we will generalize to multiple classes. So this is a schematic showing data belonging to two classes, and the two classes are shaded blue and green respectively. And their means are x1 and x2 hats. Okay, so what we desire is a direction that will amplify the interclass difference. That is, it will exaggerate the differences between the two classes. That's what is desired. Now, what does PCA do? PCA will simply maximize the variance. It will find a direction W that will maximize the variance. And this won't work in our case because if you maximize the variance, then you're also increasing the overlap between the two classes. Note that in this schematic, I've shown two different oval regions in blue and green, but the data from each category could actually cross the blue ovals and move on to the blank side in each case. It could be in Gaussian distribution. So this oval is, this overlap is just for explanation purposes. Okay, so what happens is the overlap is too high also, because when you spread out, when you increase the variance completely disregarding the classes they belong to, then you're automatically also increasing the overlap between them, which we don't want. How about maximizing the square difference between the mean projections? So you have x1 and x2 are the means of the two classes, and W is the direction, and so M1 and M2 are the projections along the direction, and our goal is to find a W that maximizes the square of the differences between M1 and M2. Will that work? Let's say visually this one is the way W that gives you the maximum of M1 minus M2 squared. So what if we decide to maximize the square difference between the means of the projections? Here, x1 hat is the mean of the first class, and its projection is M1. Likewise, M2 is the projection along this direction W of the second class mean, and so M1 minus M2 squared is what we want to maximize, and turns out that this W gives you the direction along which the difference between the projected means are maximized. Will this work? It looks like it won't work that well either, because you see there is considerable overlap here, although the distance between the two projections, the projections of the means are high. So that this is very high, this arrow. However, there is some overlap. And from another view, why do we get such overlap? That's because when we are trying to maximize the differences between the means, we are indirectly also increasing the scatters S1 and S2, the scatters of each class along that direction, this direction W. So we are increasing the scatter. I am refraining from formally defining scatter right now. So in Fisher's linear discriminant analysis for two classes, as I told you, what's desired is we want to amplify the differences between the two classes. And so just maximizing the square differences between the projected means didn't work. However, it will do a good job because in the last figure we saw that it did manage to, when you do the maximization, it sort of worked. So let's see how to refine that further. So we do this maximization, but we simultaneously minimize the projected scatter within each class. S1 square plus S2 square. Again, I'm not defining what is scatter. So we simultaneously maximize the difference between the projections and minimize the scatter. And this is informal again. I'll define this later. So this is the direction. And so you see this is high, m1 minus m2 squared. This is the difference between the projected means, and that's high. We want that to be high. And we also want the scatters to be low as possible. That's the best way we can capture the difference between the two classes. Hence, this is what we do. We maximize the Fisher's index. J of W, it's a function of W, and that's the numerator is what we want, the difference between the projected means, square root of that. That's the numerator, and the denominator is the sum of the scatters within each class, which is this. And so by defining the Fisher's index as this ratio, JW, maximizing the Fisher index results in maximizing simultaneously the projected means and minimizing the scatter. So this is what LDA does. It maximizes the Fisher's index JW. And this is the W that we get, and so this is the direction. This line here is the direction, and the scatters are kept low along the direction W, but the differences between the mean is kept high. This is the difference between two means. That's kept high. And so given the two classes of data, WPCA gives you this direction, W, which is the argmax of the projected means difference squared, is this direction, and LDA gives you this direction. That's the best one for us. And why does LDA give you this direction? Because it simultaneously tries to maximize m1 minus m2 squared and minimize s1 squared plus s2 squared. So Fisher's linear discriminant analysis, the two-class case, let's formally begin. So the direction of projection is a vector W. We will consider two classes, Ci, each Ci is a set, and I, the subscript I in an index, which will be 1 or 2. So C1 and C2 are the two classes. I'll refer to either class as Ci. The number of samples in class I, where I can be 1 or 2, is Ni, which is the cardinality of the set C sub I. And the projections along W of the samples X sub n are X parenthesis n, sorry, Xn. The projections of those samples are W transpose Xn. Likewise, the projections of the means are W transpose xi hat, where xi hat is the mean of the ith class. And the variance we define separately for each class. So the variance, uppercase lambda I for the ith class is 1 over, by definition 1 over number of samples ni times summation of all these samples belonging to the class of xn minus x hat, xn minus x hat transpose, and there should be a index I here. So that's the variance. So now let's look at how we define scatter. So the scatter was defined in terms of quantities like this, Si squared, and I is an index for each class. And so this is equal to the summation of all sample points in that class of W transpose Xn minus Mi whole squared. What is W transpose Xn? Xn is a sample. W transpose Xn is the projection of that sample point along the direction W. And we saw earlier that Mi was the projection of the sample mean along that same direction W. So this is equal to, we write down Mi explicitly in terms of W transpose Xi hat. And then, in order to simplify later on, what I do is, although what's inside the parenthesis is a scalar, it's squared, I represent as the scalar times the scalar transposed. And then I bring the transpose inside, and then what happens is each W transpose Xn and W transpose Xi hat, when you do the transpose, you have to reverse the order, so this becomes Xn transpose W transpose, and this becomes Xi hat W transpose W. Whence we can take the W from the second factor outside, so this is this W, and likewise from the first factor inside the summation, we can take W transpose common and place it here. And since both W and W transpose are independent of the Xn's, so they can be written outside the summation, and so this is what we'll end up getting. And so this is W transpose times summation of Xn minus Xi hat, Xn minus Xi hat transpose times W. And what's inside is something that's very easily recognizable. If you divide this by 1 over Ni, the number of samples in the ith class, that will give you the covariance matrix of the ith class. And so this is Ni times the covariance of the ith class. And so this is equal to Ni times W transpose, and this is lambda I, the covariance matrix, and this is W. So we saw that Si squared is simply Ni W transpose lambda I, the covariance matrix is lambda I times W. And there's another simple way to look at it. Now, this is just a reminder. We did it when we were doing PCA. So if the direction of the projection is W, any arbitrary direction W, the covariance matrix of the multidimensional data is lambda. Then we learned in the last lecture that the projection of the the variance of the projected points along the direction is W transpose lambda W. Okay, so if the direction of the projection is W, the covariance matrix is lambda, then the variance along the projection is W transpose lambda W. Now let's apply this knowledge to what we got. So the earlier derivation can be interpreted this way. Let's look at what's here. This is a summation of all sample points within class I of the W transpose Xn minus Mi squared, and W transpose Xn is the projection of a sample along direction W, and Mi is the projection of the class mean along that direction W, and that we squared, and this summation therefore can easily be recognized to be Ni times the variance along the projected direction. So in other words, what's inside this red box here is Ni times the variance of the projected points in class Ci. Now, this variance of the projected points was, we saw, equal to W transpose lambda I W, and so Ni times the variance of those projected points would be Ni times W transpose lambda I W, and so you can see that what's in this box is equal to this, which is also equal to what's in this box. Therefore, we have another way to look at our derivation which we just did a moment earlier. So we've seen the Fisher's index. The numerator is m1 minus m2 whole squared, and the denominator is s1 squared plus s2 squared. Now let's look at the numerator m1 minus m2 squared closely. m1 and m2 are the projections of the class means x1 hat and x2 hat along the direction W, which is equal to, now using the same trick as before, even though this is a square, in what's inside this parenthesis is a scalar squared, I rewrite that, not shown in this figure, I rewrite that in terms of the scalar times the scalar transpose, and eventually what I'll end up getting is this. So the numerator is W transpose xi hat minus x2 hat, xi hat minus x2 hat transpose W, which is equal to W transpose SB W, where SB is defined as the between class scatter or between class scatter matrix, and that's this. So x1 hat minus x2 hat, x1 hat minus x2 hat transpose is equal to my between class scatter matrix. That's the numerator. So the numerator is W transpose SBW. Now let's look at the denominator. This is the Fisher's index, and I've already seen that each SI squared is equal to Ni, the number of points in class I, times W transpose lambda I times W. This we defined earlier, and so the denominator S1 square, where each S1 square and S2 square can be expressed in this form, so the denominator is equal to, using this same equation, N1 times W transpose lambda 1 W plus N2 times W transpose lambda 2 W, and we can take W transpose outside and W outside, leaving us with W transpose of N1 lambda 1 plus N2 lambda 2 W. What are lambda 1 and lambda 2? The covariance matrices. So this is equal to, we define this as W transpose SW W, where SW is the within class scatter matrix given by SW equals N1 lambda 1 plus N2 lambda 2. So we have to minimize with respect to W, the vector W, the direction of this is JW, the Fisher's index, which is W transpose SBW divided by W transpose SWW, where SB is the between class scatter matrix, which is x1 minus x2, x1 hat minus x2 hat rather, times x1 hat minus x2 hat transposed. And the within class scatter matrix SW is n1 times lambda 1 plus n2 times lambda 2. So the Fisher's index is given and we have to maximize it. In order to maximize, we have to differentiate it and equate the derivative to 0. So what's the derivative of the JW? It's a vector, therefore I'm using the del here and differentiating with respect to W. What I have is denominator squared, and here in the numerator what we have is this is denominator times derivative of the numerator, this is the numerator, minus of numerator times derivative of the denominator. And it can be noted that both SB, the between class scatter matrix, and SW, the within class scatter matrix, they're both symmetric matrices, and so their derivatives can be easily done. So this is the del W of W transpose SBW is simply SBW, and del of W transpose SWW is simply SWW here. And so this is what we have, and W transpose SWW SBW minus W transpose SBW W SWW, which is equal to 0. And if this is equal to 0, then the numerator must be equal to 0. Since the numerator is 0, we just saw that the numerator was equal to this expression here. It's W transpose SWW times SBW, W transpose SBW times SWW. And that's equal to 0. Now note that W transpose SWW and W transpose SBW are scalars, whence SBW can be expressed as the ratio of the two scalars times SWW. Or if you look at this ratio, this is SBW in the numerator and W transpose SWW in the denominator. This is nothing but the Fisher's index. And so what we land up with is SB times W equals JW, the Fisher's index, times SWW. So this is the solution. We arrive at this expression. If W is the required direction, SBW should be equal to JW, the Fisher's index, times SWW. The Fisher's index is a scalar, and writing that scalar as lambda, what we have is SWW equals lambda times SWW. This is SBW, excuse me. SBW equals lambda times SWW. And this, so why not solve it this way? We can simply write this expression as SW inverse SBW equals lambda W. The problem is the rank of SW, the within class scatter matrix, is less than equal to n, and n is the number of sample points. Why? Because it's a summation of n different rank 1 matrices. And what if D, the number of dimensions, is greater than n? And sometimes this is what happens. The samples, the number of samples are n, but the dimension of each sample is very high. Each sample could be, for instance, an image of a face. And that's something we'll look at later. So SW is not invertible. So this is what we'll end up with. So this form here is the definition of the generalized eigenvalue eigenvector. This is the definition, formal definition. Given a pair of matrices A and B, AV equals lambda BV is the definition of eigenvalue eigenvector. V is the eigenvector and lambda is the corresponding eigenvalue. And in order to maximize this, we need lambda to be as high as possible. And so this definition fits the definition of a generalized eigenvalue eigenvector. W is an eigenvector, generalized eigenvector, and lambda is the generalized eigenvalue of the matrix pair SB and SW. And so we want to maximize the Fisher's index, which is lambda. So we want, in other words, to set the eigenvalue eigenvector to the largest pair. So what we have is V equals W1, the largest generalized eigenvector of SB, SW, and lambda 1 is the corresponding largest generalized eigenvalue. And this is the reason why the matrix earlier had a rank that was N, which could be less than D. Lambda is the covariance matrix, and it's a summation of n different terms. Each term is xn minus x hat, xn minus x hat transpose. So this is, each of these is of rank 1, and when you add n of these, this matrix can have a rank at most n. So the rank of lambda is less than equal to n, and the scatter matrix is nothing but n1 lambda 1 plus n2 lambda 2. So the scatter matrix cannot have a rank which is more than uppercase n, and the number of dimensions could at times be more than n. So in those cases, since SW, if you look at the definition of SW, it's a D by D matrix, and its rank is at most n, and if D is more than n, obviously it's not full rank. So now let's extend our knowledge to C classes. So we have multiple class discriminant analysis, and the between class matrix is defined as before, except instead of just two terms, now we have one term for each class. So the between class matrix is summation of I, summation for each class times Ni, the number of samples belonging to class I, times xi hat minus x hat times xi hat minus x hat transpose. This xi hat is the mean of the samples of the ith class, and x hat is the mean of all the samples. And the rank of this SB is, since it's a summation of C different rank 1 matrices, the rank of SB is always less than equal to C. In fact, a little further investigation would show you that the rank of B is less than equal to C minus 1. The within class scatter matrix is this double summation, summation for each I equals 1 through n of summation within that class I, summation of all the sample points of xn minus xi hat, xn minus xi hat transpose. And once SW and SB are obtained, one has to solve the generalized eigenvalue eigenvector problem. SBW equals lambda SWW. W is a generalized eigenvector, lambda is a generalized eigenvalue. And unfortunately, we cannot seek more than C minus 1 W's. Why so? Because the rank of SB is less than equal to C minus 1, and what then happens is the other remaining lambdas will turn out to be zeros. So this is what we do in Fisher's linear discriminant analysis for multiple classes. The projection matrix is what we are looking for, and it has, since we can only compress up to C minus 1 dimensions, not less than C minus, not more than C minus 1 dimensions. So what we are looking for is vectors, C minus 1 column vectors, W1 through W sub C minus 1. And it turns out, I'm not going to prove it, it turns out that the generalized Fisher index is equal to the determinant of W transpose SBW. Since W is now a matrix instead of a vector, W transpose SBW is a C minus 1 times C minus 1 vector, and similarly W transpose SWW is also a matrix, and so the generalized Fisher index is the ratio of the determinants. The generalized eigenvalue eigenvectors are defined like this, and the solution W, this is the projection matrix, the solution is given by taking together the columns, the C minus 1 columns of the as the generalized eigenvectors of SB, SW. And we cannot seek more than C minus 1 eigenvectors, which is a fundamental limitation of LDA. So let's see how we can apply PCA and LDA in combination for face recognition. It turns out that combining PCA and LDA gives you a really great algorithm for face recognition, and it's commonly used as an exercise in many different courses on machine learning or dimension reduction or even statistics. Anyways, so what we have here is different faces, Fn, n equals 1 through n, so we have a lot of sample faces, and each face is obviously a matrix. The length and breadth are L and B, so it's a L cross B matrix of pixels, and you have to convert that to L dot B, LB cross 1 vector. So this matrix is being converted to a vector, and LB cross 1 vector, and using our notation, LB equals D. So a 50 by 50 matrix, L will be 50 and B will be 50, and so this is 2500 by 1, or D is 2500, and those are the samples. So each sample is a 2500 dimensional column vector. The number of classes is C, let's say, and here's the approach. First, we use PCA to reduce from D dimensions to n minus C dimensions. And n is, think about 72, and C is the number of classes, which is I think 10. And then the next step is, once PCA is done, then the reduced dimension vectors are further compressed from n minus C dimensions to C minus 1 dimensions using LDA. And after this step, we are left with C minus 1 dimensional vectors. Then what should be done? Use nearest neighbor approach to classify in C minus 1 dimensions. Nearest neighbor or any other classification algorithm will do. So here are the steps, the PCA steps. Step 1 is we do the PCA. So the first step is compute the total scatter matrix ST. In PCA, we normally use the covariance matrix, and the total scatter matrix is simply n times the covariance matrix lambda, and this is the definition of the scatter matrix. So we call it, just to keep in adherence and conformity to the other matrices that we used in LDA, we call this matrix ST the scatter matrix, and we use the scatter matrix instead of the lambda, same thing. And then using the eigenvectors of the scatter matrix, the total scatter matrix, we construct WPCA. And the columns of WPCA will give you the directions of the projections. These are the principal components. And then the raw data xn, which each of them was a d-dimensional vector. After we do this operation, WPCA transpose xn, that will give us a lower dimensional n minus c dimension vector yn. So we'll have uppercase n samples of yn. Each of these yn is n minus c dimensions. So the next and last step rather, is after applying PCA. Why did we apply PCA? Actually, that's because all the phases are highly correlated. And so the PCA extracts n minus c dimensions that are orthogonal, and then the next step, we use LDA to maximize the differences and reduce the dimensions of the samples to c minus 1 from the earlier n minus c. So how do we do that? We compute the n minus c by n minus c matrices SB and SW, and they are defined previously. This is SB and this is SW. And then we construct WLDA using the c minus 1 generalized eigenvectors of SB and SW, and then we do the dimension reduction. This vector here should be y of n, not x of n. That's a typo. So z of n is equal to WLDA transpose y of n. What's the dimension of WLDA? It's n minus c by c minus 1. And with that, we have very low dimensional vectors z of n, one for each image, and then we can apply nearest neighbor methods or any other method to compute the to do classification. The end.